Um, and as always, if you have questions about something, try to let me know sooner rather than later. Um, and yeah. Um, from there, um, I was just going to get into our lecture for today. Yesterday was lecture one, and we didn't cover everything that I had in my slides. So even though like it's the title of this is lecture two, I'm starting with the slides that we're finishing up on lecture one, and then we'll get into the lecture two material. All right. So last time that we were here, we talked about some of those fundamental definitions. We talked about macroscopic cross sections, microscopic cross sections. We talked about beam intensity and showed how that intensity exponentially decreases through a slab. And today I wanted to kind of cover some more of those odds and ends before we get into some of the kind of continuing introductory stuff, mostly relating to the fission process and talking about more about conservation equations. So last time we were here, we introduced this definition for the macroscopic cross section, that the macroscopic cross section big sigma x is for a material is the number density of that material times the microscopic cross section for that material. And then x can be any reaction. It could be fission or absorption or capture or lots of other things. Um, in this definition, the most complicated part is due to the microscopic cross section, because that's where the dependence on the relative speed between the neutron and the nucleus is involved. So that dependence is really important. And part of the reason that it's important is because without that dependence on that relative speed between the neutron that's coming in and the nucleus that it's interacting with, our reactors would actually be less safe. So this adds to the safety. If we didn't have this, the fact that we do have this makes our reactors safer. Um, in terms of thinking about temperature dependence of these cross sections, what we want to kind of realize is that, like, even in this simple picture where you've got like neutrons coming in, hitting some slab of material, like maybe this is a piece of iron or a piece of uranium, this piece of material is made of atoms. Even like this desk, if you were to like zoom in really close to see the individual atoms of the desk, it would kind of look like this cartoon where those individual atoms aren't just stationary, but they're actually kind of vibrating in place based on how hot they are, based on their temperature. So that's point one, is that nuclei wiggle. And you can think of those wiggles as little harmonic oscillators where like the bonds between the atoms are kind of like almost like a spring, and those nuclei vibrate in place. Um, Generally, we can make a simplification, which is that those vibrations within the lattice or within the structural materials that we're talking about can be treated as isotropic. Do y'all know what isotropic means? ISO is same, and then sorry, uh, that would be isothermal. Tropic, you're thinking of it's like a directional thing. So isotropic means same in every direction. So that means that like if we have an isotropic material, it doesn't actually matter if the neutrons are coming in on this side or on that side or on that side. If the material is vibrating isotropically, then it looks the same to a neutron that's approaching it from any direction. And in that case, if we think about these nuclei as vibrating isotropically, that means that we can characterize the velocity distribution of the nuclei in our material as following a Maxwellian distribution. So it's well characterized by a Maxwellian distribution. The vibrational velocities are approximated by this distribution, and the Maxwellian distribution only depends on the temperature of the material. So it's a distribution which only depends on the temperature of the material. So if the material is isotropic, then the neutron looks the same to the neutron from any direction. In that sense, it means that it's not actually the relative, or that means that instead of really needing to talk about the relative velocity, which includes the speed and the direction, we actually only have to talk about the speed of the incident neutron. So like in general, if we were to write our microscopic cross section, it's technically a function of the velocity of the neutron and the velocity of the atom that it's interacting with. So this is neutron. This is the atom or the nuclei that our neutron is interacting with. That's what the microscopic cross section would depend on. But if we assume isotropic for the nuclei, then instead of having to talk about this microscopic cross section in terms of the velocity of the neutron, we can think of it as the speed of the neutron. And it also means that we'll have the velocity of those atoms. And then the velocity of those atoms can be well characterized by that Maxwellian distribution, which means that instead of having to think about the velocity distribution of all of those little nuclei in our material, we only have to think about one thing, which is the temperature. So once we assume a Maxwellian, then our cross section, our micro cross section, becomes just a function of the neutron speed and the temperature of our material. Now, if I know the speed of the neutron, then I can also directly talk about the energy of the neutron, even just using like a classical like 1/2 mv squared formula for the kinetic energy. So that means that it's equivalent to talking about the energy of the neutron instead of the speed of the neutron. Energy is the more convenient term to use, and there's a one-to-one relationship between the speed and the kinetic energy of a neutron. And so generally, this is what we're going to think about for the dependence of our microscopic cross sections. If we make these assumptions, then these microscopic cross sections really only depend on the energy of the neutron. I can put a subscript in here just to remind us that it's the energy of the neutron. And it's common to just drop the temperature argument from that expression because when you get a cross section in this class, we're going to assume that that cross section has already been properly averaged over the range of nucleus vibrations. So usually we'll just drop the temperature argument, and that's kind of the assumptions that we're going to have baked into cross sections that we see in this class. Um, the most important kind of phenomena that relates to the temperature dependence of these cross sections is a phenomena called Doppler broadening. We saw last time, so this would be a plot of a cross section of a nucleus. And if you think about the energy range, this would be like low energy, this would be like kind of the intermediate energies, and then these would be high energies. And in this intermediate range, you have this resonance region where the cross section is doing all this crazy stuff. And what we want to imagine is that if we were to peak on any one of these individual resonances, we would see a plot that looks something like this. T1 is like some initial temperature, and then we want to imagine that we've got this temperature, we're measuring cross sections, and then we're heating that material up. And then we're measuring how that cross section changes as we heat it up from T1 to T2 and then to T3. And so what we can see is that these cross-section resonances, the magnitude decreases and the resonance itself broadens. So like the individual areas on these plots would be more or less the same, but you're spreading out that resonance. And so this phenomena, where we have an increase in temperature causing these cross sections to broaden, is called Doppler broadening. Doppler broadening. And in practice, what this means is that if your material temperature starts heating up and these resonances broaden, then E0 is like the energy of the neutron that would be most likely to the energy of the neutron where this reaction cross section would be the highest. And that if you have if you have a neutron coming in, it's gonna preferentially have a cross section that's very high if it's right at this energy E0. And as that material temperature heats up, your probability of interaction away from that E0 becomes larger. Like if we were to compare the an energy range kind of away from E0, then these T's at these points, the you get a broader probability for different neutrons to have this interaction. Um, and so basically what it ends up meaning is that these broadening of the resonances mean reactions are more likely, and in that intermediate energy range, the reactions that happen are capture reactions. So the temperature increases, these cross sections broaden, and it makes absorption, like parasitic capture of the neutron more likely. And so if the neutron is getting absorbed but not causing a fission due to the broadening of these resonances, that means that when temperature goes up, our reaction rates actually end up, or at least our fission reaction rates, end up going down. So the temperature goes up, we get more capture reactions. That means that our fission rate and our power would actually end up going down. And that's an example of negative feedback. This phenomena provides negative feedback, which is a good thing. The opposite would be that if temperature went up, our fission reactions went up, and then you would have a cycle that would go out of control. So this phenomena allows us to have control of our reactors because if temperature goes up, it actually makes effectively our fission rates and our reactivity go down. And this phenomena happens away from resonances too. Oops. It's just more prominent at in that resonance region. And we'll talk more about this later. This probably isn't like immediately obvious right now, but because we're talking about cross sections and temperature dependence, it's a good point to bring it up before we talk about it more later. So the next thing I wanted to talk about is just the fission process and really talking more about the distribution of probabilities that come out of fission. So if we think about like a simple fission reaction where a neutron comes in and it hits uranium-235 and then makes uranium-235 fission, then we're going to get fission reaction byproducts out of that. Um, when a uranium atom fissions, what would some of those byproducts be? What kind of things are going to come out immediately after that fission reaction? Yeah, we can call those the things that come immediately out, we can call them fission products for sure. That uranium-235 is going to split into like two pieces. So those would be our fission products. Do we get anything else out of a fission reaction? We get and energy is based on the particles that are coming out of it. So those fission products take away energy. Other particles, what's the with a chain reaction, it's a neutron comes in and then more neutrons come out, right? So neutrons would be another thing that are emitted from this reaction. And you get all kinds of other stuff too. You end up getting things like neutrinos, you get gammas, you get beta particles. You get a lot of stuff that comes out of these reactions. And so when the focusing specifically on the neutrons coming out of that fission reaction, there's a couple things that we want to know about the neutrons coming out of fission. The first thing is that the neutrons that come out of fission are independent of the initial neutron energy that caused the fission. So these neutrons are independent of the incident neutron energy. let me, I'm gonna move this over so I'm not writing on top of the title of this graph. Incident neutron energy. So that's point number one. It doesn't matter the energy of the neutron that comes in. The neutrons that come out are going to be independent of that incident energy. Um, these neutrons that come out of fission are also going to be emitted isotropically. They're emitted isotropically. So there's no preferential direction from which neutrons come out of fission. They're not biased towards one particular direction. It's kind of going to be emitted in the same amount in any direction. And those neutrons that come out of fission, they are going to have a distribution of energies at which they could be coming out of the fission reaction. So they have a distribution of emitted neutron energies. Um, that distribution of the neutrons that are coming out of fission, we give that energy distribution a name, and it's called the fission spectrum, which is the plot, one of the plots that's shown on the right. So we call this distribution the fission spectrum. We use the symbol chi for that fission spectrum, and it's a function of the energy of the neutron. It's a function of the neutrons. This E is the emitted energy. And this is a probability distribution function. So it has units of inverse energy, like 1 over electron volts, or 1 over mega electron volts, or 1 over joules. Um, and oops. And so that's what this plot is showing. The red line is the fission spectrum, and these are both for uranium-235. This is like an analytical, or really it's like a curve fit to what this fission spectrum actually looks like. And what it shows is the probability that neutrons, it's a probability that a neutron coming out of fission has a particular energy. So as we can see, the probability that a neutron comes out with zero energy is basically zero. This distribution and this distribution increases up until around this point, and that point is at about 1 MeV. At approximately 1 MeV is where this distribution peaks. So that means that if you have fission reactions, neutrons are going to be coming out at all kinds of different energies, but it's most likely that they come out around 1 MeV. And then you get you could have neutrons coming out at 4 MeV, at 3 MeV, at 6 MeV, and higher energies become less and less probabilistic. So the likelihood that a neutron comes out at 10 MeV is fairly low. Going further to the right, it becomes even less likely. So that's the fission spectrum. It's basically the probability density of neutrons coming out at a specific energy. And then the cumulative distribution function, the CDF, is the integral of the PDF, and it basically is tallying up the probabilities such that what you can use the CDF for is to say, at some range of energies, how many neutrons are most likely to come out of that range. So like if we look at this distribution up to like, this is a good number to pick because it's on our axis. Oh, and I'm looking at the wrong side. Um, if we think about 0 to 6 MeV, this distribution is like pretty close to its maximum. It looks like it's about 0.9. This would be about 0.9 or so. So what that is telling you is that if you think about the number of neutrons coming out of these fission reactions, 90% of them are going to be born with an energy less than 6 MeV. And so, yeah, that's a PDF and a CDF for our fission spectrum. And this is the thing that tells us about how the neutrons' energies are distributed as they come out of fission reactions. So we had been talking about beams, like neutron beams last time. And I think it's important to start getting away from the neutron beam and to start more talking about like the neutron distribution within some system, like within a reactor. And so to do that, we are going to generalize what we talked about before with that thin target case. Um, and we're going to make the assumptions that we had made that we were just talking about in terms of the nuclei vibrating with that Maxwellian distribution at some temperature T. So we had already seen that the collision rate is the intensity I times the total microscopic cross section, and we can write that now as a function of the neutron energy, E. Also, there was a multiple, oops, this was also being multiplied by the area of the target and the thickness of the target. This was like that thin target collision rate that we started with in lecture one. And if I have an area of my target and I have a thickness of the target, the product of the area and the thickness of that material is going to give me what geometric quantity? Volume, right? So then we can think of this as the intensity times a total cross section times the volume of the material. When I do V, I like to do like a capital V with a line through it. So that's my notation for volume. That will hopefully help us differentiate from little v, which would be like for a velocity. Sorry, but hopefully that makes it a little bit clearer. So this is the expression for a collision rate. If I wanted a collision rate density, so this collision rate is going to have units of like reactions per second. If I wanted to make this a collision rate density so that it was reactions per unit time per unit volume, I would just take this expression and I would divide both sides by the volume. So if I divide this volume out on both sides, then I get the collision rate density, which is the collision rate divided by the volume. And then it would just be the intensity I times that total cross section. And this collision rate density has units of reactions per unit time per unit volume. That's what the term means. Collision rate density or collision reactions. It's a rate, so it's per unit time, and it's a density, so it's per unit volume. And if this is the units of the collision rate density, we also know the units of the total macroscopic cross section. We talked about this last time. It's the number of reactions per unit neutron distance traveled. We know that that's the definition of the units for the total cross section. And if this is what the collision rate density is, then we can put these two things together. And really, we called it a neutron distance traveled. So we could even just add in the neutron there to just remind ourselves that it's based on the path length of the neutrons in that material. Um, Based on these two things, we can work out what the units of this intensity in this non-beam case should have. So if we ultimately want collision rate density units on the left-hand side, then this intensity has to have neutron centimeters on the top, and it needs to have centimeters cubed per second on the bottom, such that if these neutron centimeters canceled with these neutron centimeters, then we would overall have units of collision rate density on the left. So that kind of leads us to a different interpretation of how we were thinking about the intensity before. Before we had talked about the intensity as like crossing rate per unit area. This definition of the intensity is looking like neutron path length per unit volume and per unit time. The distance traveled by those neutrons per unit volume and per unit time. And so that interpretation might seem weird, and I want us to think a little bit more about investigating that to see if it makes sense. So, in this case, we're going to be looking at a bunch of neutrons like in a box, and we're going to assume that these neutrons are monoenergetic. So that means that they all have the same energy. And we're also going to assume that they're isotropically moving around, so they don't have any preferential direction in which they're moving. They're all moving in random directions. And we're going to define some quantities. We're going to use little n for the neutron density. So that's the number of neutrons per unit volume in this box. We're just going to use a little v for the neutron speed. This box is going to have some control volume. We'll use dv with a line through it for the control volume. And then we're going to track these neutrons over some time interval dt. So the first thing that we want to think about, if we're trying to see if this definition of path length rate per unit volume makes sense, then we want to think about in this little box what would be the total path length made by all of these neutrons. And that total path length would be the path length made by one neutron times the number of neutrons that are in the box, since they're all moving at the same speed and they're all moving isotropically. So with these quantities, what things would I multiply together to get the path length made just by one neutron? Path length meaning just like the distance or like the displacement that a neutron has in that time interval dt. Yeah, so we've defined these quantities on the left, and I was just wondering which of these quantities would we multiply together to get the distance traveled by one neutron? Yeah, distance. Thinking back to like, yeah, you would multiply the speed and the time interval, right? So v for the speed and dt for the time interval, right? Because v is meters or centimeters per second, and then the time interval is seconds. You multiply those together, you get the centimeters traveled by that neutron and that time interval dt. And then what would I multiply together to get the number of neutrons in the box? N and dv, right? If I've got the neutron density and then I hit that with the volume, then instead of having neutrons per unit volume, I just have the total number of neutrons in that volume. And so if that's my expression for the total path length, then if I wanted to make this a path length rate per unit volume, then I would take both sides of this equation and I would divide through by the thing that's giving me time, and I would divide through by the thing that's giving me volume. So now what I have on the left side is the total path length per unit time or per unit volume, which is the definition of the path length rate per unit volume. And then this dt is canceled, this dv is canceled. So all we have left on the right is the product of the speed of those neutrons and the neutron density in that material. And so this right here, the speed of those neutrons times the density of those neutrons is what gives us this path length rate per unit volume. And in nuclear engineering, this is a very special quantity called the scalar flux. So N times V is the fundamental definition for the scalar flux. So in this context, the scalar flux is what we want to think about in terms of having those units of path length rate per unit volume. And that's the way that I like to think about the scalar flux. It's got units of neutron path length per unit time per unit volume. So you're adding up the distance traveled by all of those neutrons, and then you're looking at that per unit on a per unit time basis, which makes it a rate, and on a per unit volume basis, which makes it a density. So sometimes this is referred to as a path length rate density, and that's all that it means. It's just based on how we've kind of set things up and based on the units. So this is like an alternative description or way of thinking about the scalar flux. You can think of it as a intensity, like as a number of neutrons crossing some unit area per unit time, or you can think about it as the track length made by all of the neutrons in some box in some volume per unit time. This is a really important equation. We definitely want to keep this one in mind. both in terms of the definition for how we can compute the scalar flux and also in terms of this physical interpretation for what the scalar flux means. So that is the scalar flux. It's going to be, in general, a function of the position and time, and it represents total distance traveled by the neutrons of all energies, moving in all directions per unit volume per unit time. Um, and so if we go back to the beam intensity definition, if those neutrons, instead of bouncing around isotropically in a box, were just moving in a straight line like in a beam, then the scalar flux and the intensity have the exact same interpretation. Um, so this is like the quantity that's really nice to work with because we use the scalar flux to compute reaction rates. But in general, the scalar flux can be more complicated, or at least the fluxes in a reactor are more complicated because in reality, the neutrons have a distribution of energies in our reactor, and they also have a distribution of velocities as well. So, sorry, they have a distribution both in energy and in terms of the direction in which they are moving. So there's kind of like a hierarchy of neutron fluxes that we can talk about to better understand where the scalar flux is coming from. And so the most this right here, this picture is like the most complicated way that we could think about what the neutrons in our system are doing. So we've got like traditional XYZ coordinate axes, and then we've got all these little white dots are like the neutron field at some position R in this coordinate system. And then at that position R, we're drawing this little control volume, this little D3R or DV, which has like a little DX, a little DY, and a little DZ. And the neutrons in this little box, they could have a range of energies. So like if we think about like an energy axis, these neutrons in this box have some little energy dE, and they might be moving in some particular direction omega. This little omega is like the unit direction vector that points to which way those neutrons happen to be moving. And if we want to describe this omega in a 3D coordinate system, we need two angles. We need an angle theta, which is like a polar angle from the vertical, and we need this other angle little phi, which is like an azimuthal angle that goes around that wraps around that vertical axis. And so the quantity that we could use to describe this most detailed way that the neutrons are distributed would be called the angular flux. And so we use the Greek letter psi for the angular flux. It's like that little pitchfork looking thing. And psi depends on the position. It depends on time. It depends on the energy of the neutrons, and it depends on their direction. So that omega vector is the direction vector of these neutrons. And the angular flux has very similar units to the scalar flux, but it's a more complicated distribution. So it's got units of neutron path length per unit volume and per unit time, but it's also a distribution in energy. So it has per EV units and it has a distribution in direction. So it also has per unit steradian. SR is the steradian, which is the unit for solid angles. So this SR is called the steradian, which is how we describe solid angles. So that's the most complicated way that you could talk about neutrons in a reactor would be with the angular flux. And there's an equation that talks about, like, there's an equation you could solve for the angular flux, which is called the neutron transport equation. We're not going to deal with transport in this class. So the angular flux is kind of like a grad school level topic. I'm just introducing it this far so that we can understand the hierarchy of the different scalar fluxes. So if I wanted to get away from the angular flux and simplify this distribution, what I could do is if I knew what that angular flux was, I could take it and I could integrate over all of the neutron directions. I could integrate it over all of the solid angles, which would mean over 4 pi. And that would get rid of the angular dependence. So if I were to go from 0 to 4 pi, and I were to integrate that angular flux, which is a function of position, time, energy, and direction, and I was integrating this with respect to direction, this is basically just saying I'm taking that quantity, that angular flux, and I'm integrating it over all directions. That's going to remove the angular dependence, and that's going to give me something called the energy dependent scalar flux. So it's going to have units of position, time, and energy. The angular part is eliminated when I integrate over all directions. So this thing right here is the energy dependent neutron flux. And it is also a distribution. It's a path length rate per unit volume and also per unit energy. In our class, we will deal with the energy dependent neutron flux. So this is how you would get that if you had a more complicated distribution. And yeah, so that is what we're gonna need to be comfortable with. And we'll get more into energy dependence later in the course, but I think it's good to just start with this, use this as a starting point to move forward. And if we can integrate the angular flux over all directions to get a more simplified distribution, we could also integrate the energy dependent flux over all energies to simplify that distribution. And that's how we would get the scalar flux. If we took that energy dependent flux and we integrated it over all energies, so we're taking that energy dependent flux, that flux is as a function of position, time, and energy, and we were to integrate it over all energies, that would give us the plain old scalar flux, which would just be a function of position and time. So that's part of the kind of hierarchy of the fluxes. The scalar flux is the easiest distribution to work with because it only depends on position and time. And there's a lot baked into it because of the fact that it comes from integrating over all directions and integrating over all energies. So when we talk about the scalar flux, sometimes it's referred to as the total flux because it is talking about the path length rate per unit volume made by neutrons of all energies and that are moving in all directions. So this is kind of like a table that explains that hierarchy of fluxes and the governing equations that come from it. And in each of these cases, you can talk about that flux as being a product of a density and a speed. It's just that the density is more complicated depending on which type of quantity we are talking about. So like I said, in our class, we're pretty much exclusively going to deal with the total flux and the energy dependent flux. It's just an unfortunate thing that in this field, we use the same symbol for both the scalar flux and the energy dependent scalar flux. Sorry. But you can usually tell from the context or by the units which one you're given. Like if you're given some scalar flux and it has an energy argument within it, then you know that it's an energy dependent flux and then it has those per EV units in the bottom. Whereas if you get a flux and it just has path length rate per unit volume, then you know that it's the total flux and that the energy has already been it's already been integrated over all energies. Um, so just like a couple points to make about our fluxes. If you had a nuclear reactor and you were to know what the energy dependent scalar flux is, um, there's a couple questions that you might want to ask, or you might try to ask. One of those questions would be, can we figure out how many neutrons in a reactor have exactly 1 MeV of energy? What do y'all think? No, right? Hopefully we're thinking no. And the reason is because this is a distribution. The energy dependent flux is a contains information about the distribution of neutron energies. And so in a distribution, you can't really say how many neutrons have a specific energy, like because 1 MeV, you could think of it as 1 MeV. Another way of saying that is has exactly 1.000000000 MeV. And that's just never going to happen. There's always going to be some distribution, and therefore you're not going to have anything at exactly 1 MeV. So you can't specify a single value or a single point with a continuous distribution. But what you can say is how many neutrons have a specific energy range. So we can talk about a range. For example, how many neutrons have an energy within 1 MeV and 1.1 MeV. That's something we could talk about, but we can't talk about evaluating it at a specific point. The next thing that we might want to ask is, what is the path length made by these neutrons at some specific point? And that's another one that we can't really talk about. And the reason you can't talk about a path length rate at some point is because path length means that you're covering some amount of distance. So you can't cover distance at a finite point. So no for this one too. You can't cover distance over a point. You can't cover distance over a point. Um, but so it doesn't make sense to say what's the path length rate at a particular point, but you can say what's the path length rate density at a point. That's the thing that it does make sense. So you can talk about the path length rate density. So like in other words, if you have the scalar flux, you can evaluate that at a point and it will tell you about the path length rate density of the neutrons at that point. But you can't then take the neutron path length, you can't take the scalar flux and then integrate that over volume. That's kind of what this question is asking about. That wouldn't really make sense. Okay, so those are just some important points about fluxes. Um, that kind of leads us into the concept of a reaction rate density. So the reason that we use the flux is because we use it to compute reaction rates. If we assume that our neutrons are distributed isotropically, then the energy dependent flux is like the most complicated distribution we're going to work with in this class. And if we assume that those nuclei in our material have that Maxwellian distribution and that we've already averaged over the range of those nucleus velocities, then we have a very simple or relatively simple equation that we can use to talk about the reaction rate density. So the reaction rate density is what you get if you integrate over all energies the scalar flux, the energy dependent scalar flux. So flux is as a function of position, time, and energy. And you multiply that with some macroscopic cross section, which is a function of the neutron energy, and then you integrate that over all energies. So if this quantity right here, the energy dependent flux times a cross section, this is like our energy dependent reaction rate density. In other words, if we think about the units of the scalar flux, the energy dependent scalar flux, it has units of path length per unit volume, per unit time, and per unit energy. And then the macro cross section has units of reactions per unit neutron distance traveled. And then dE is what contains our energy units in EV, such that if we think about these quantities based on their units, we can see that this works out to give us units of number of reactions per unit volume and per unit time. These neutron path lengths cancel those neutron path lengths. These EVs cancel those EVs so that we have units of reactions per unit volume per unit time, which is the definition of a reaction rate density. And physically, that is the units kind of tell you what a reaction rate density means physically. It's the expected number of reactions due to neutrons of all energies per unit volume per unit time. And yeah, and I guess we can think about this reaction rate density as being a function of position. Oops. That reaction rate density just depends on position and time because we've effectively integrated out all of the energy dependence by taking that energy dependent reaction rate density and integrating over all energies. Um, so yeah, that's like kind of the fundamental definition of reaction rate density. And the other kind of way that you can just think about the reaction rate density, once you've integrated over all energies, that's equivalent to just having your scalar flux times a macroscopic cross-section. Um, so that's the other way that we can kind of think about the reaction rate density. So it kind of depends on what you're given. If you're given the energy dependent flux and you need a reaction rate, you're going to have to take that flux, multiply by the cross section of that reaction, and then integrate over all energies. Whereas if you just have the scalar flux, then you can just go ahead and multiply that by the cross section of interest to get the reaction rate density for whatever type of reaction your macroscopic cross section is describing. And so just like in general, that was just for a general reaction rate. You can talk about different types of reaction rate densities depending on what cross-section you have. If you have a fission cross-section, then that would be your fission reaction rate density. If you have a scattering cross-section or an absorption cross-section, that would be talking about your scattering rate density or your absorption rate density. And if we've got reaction rate density and we want to get the reaction rate, all we have to do is take that reaction rate density and integrate it over the volume. So if you've got a density and you integrate over the volume, then you can recover that reaction rate. So the reaction rate is going to be the integral over the volume of our system and the integral from 0 to infinity of that energy dependent reaction rate density. Integrating over all energies and integrating over the volume of our system. And what's inside here, if I were to just look at this part, that by itself is the reaction rate density, because we've taken that energy dependent density, integrated over all energies, and then if we take that and integrate over the volume, that's what gives us our plain old reaction rate. So this is partly why it's very important to make sure that we know the units of all of these individual quantities, because if you know the units of the fundamental quantities that we're working with, you can kind of multiply those things together to get whatever quantity of interest we are looking for. There's a couple examples that I think are really helpful for better understanding how to take these fundamental definitions and then get other quantities of interest from them. I think for the interest of time, I'm not going to work through them right now, but I made a note of where in Dr. Adams' notes you can find these examples. These are just questions about setting up the integrals that would explain how to find different quantities. So example 1, 2, and 3, those are in Dr. Adams' notes on those pages that I listed. Adams' notes are in our shared Google Drive. If you don't have access to that shared Google Drive, let me know so I can get you in there. Yeah, Adam's notes are really good. I think that's a really solid place to start in terms of getting understanding about anything that we might be confused on. And then, yeah, and then Svetkov's notes, which are kind of what this course is based on, take that and go deeper in depth. So I think part of what I try to do with this class is make us realize that the stuff that we've learned in past classes like 301 and 302, it does carry over almost directly into this class. And fundamentally, we don't actually cover that much new stuff in 304 compared to 301. We're just taking it and kind of going into more depth. So this is a good starting point to have, and these examples in Dr. Adams' notes can kind of help clarify a little bit more about how to use these definitions that we've already introduced. And so basically that covers the end of our lecture one material. And this is just a summary of everything that we talked about in lecture one. Fundamentally, we're concerned about nuclear engineering and reactor analysis. To understand what reactors are doing, we have to know what neutrons do when they interact with stuff. And that means we need to know about neutron nucleus interactions, and we need to know about computing reaction rates. So in lecture one, we kind of covered all of the fundamental information that we need to start doing those calculations. And then in lecture two, we're going to talk more about fission, and we're going to talk about using these definitions to start building up conservation statements for neutron populations. And that's what we're going to be talking about today. Using those equations to develop some equations to get reaction rates that we can use to set up conservation equations to find neutron distributions. So some other important stuff that we need to be aware of in terms of this discussion about fission is the concept of the binding energy of the nucleus. So if you think about an atom, just like a nucleus by itself, which is going to be composed of protons and neutrons, if you were to look at all of those individual nucleons, all of the individual protons and neutrons, and put them on a scale, and then you were to form that nucleus and put that nucleus on the scale, they're not going to weigh the same. The individual nucleons, are actually going to weigh slightly more than the nucleus itself. And that mass difference is given by the mass defect, which is this delta M. And the mass defect is basically defined as Z times the mass of our proton plus N times the mass of our neutron, and then minus the mass of our nucleus. And that nucleus has a particular Z and a particular A, where Z is the number of protons, N is the number of neutrons, and then A, the atomic mass, is those two put together. Sorry, it's N plus Z. So that's the definition of the mass defect, the difference between the constituents of the nucleus and the nucleus itself. And if we want to take this mass defect and convert it into an energy quantity, what would we multiply that mass defect by to turn it from mass into energy? Yeah, perfect, right? E equals mc squared. So if we take that delta M and then multiply it by c squared, that's the definition of the nuclear binding. And so physically, what that binding energy represents is how much energy you would have to supply if you wanted to take that nucleus and pick it apart and separate all those individual protons and neutrons into individual quantities. Um, and so in terms of like simplifying the calculations for the nuclear binding energy, it's very common because the nuclear binding energy is so much bigger than the electron binding energy. It's relatively easy to strip electrons away from an atom. It's a lot harder to pull nucleons out of that nucleus. And also because when you're looking at tabulated data for nuclei, you will often get the mass of the atom and not so often the mass of the nucleus. It's a common approximation to make to say that if we wanted to talk about the binding energy of an atom, it's the binding energy of the nucleus plus the binding energy of those electrons. If we wanted to make a nucleus, you supply protons and neutrons. If you want to make an atom, you have to supply protons, neutrons, and electrons. But the binding energy of the electrons is so much smaller than the binding energy of the nucleus that for all intents and purposes, this is like basically zero. And therefore, the binding energy of the nucleus is pretty much the same thing, very close to the binding energy of an atom. And so that means that we can talk about the binding energy of the nucleus as this. We're basically doing Z times the number of protons plus, or sorry, Z times the mass of the proton plus the mass of the electron plus the number of neutrons times the mass of the neutron, and then minus the mass of the atom, which is going to depend on its Z and its A. And if we take this as effectively the mass defect for the atom, and if we take that mass defect of the atom and then multiply it by c squared, that is approximately going to give us the binding energy of the nucleus. So that's just a kind of refresher on binding energy, and hopefully we've seen those definitions before. But if not, or if we'd forgotten them, that's those definitions that we would want to have. And the reason we talk about binding energy is because it's very important to understand why fission happens in the first place, and why fission and also fusion are like energetically favorable processes. Um, so the binding energy in general is just going to increase with the mass number of the nucleus, but it's not constant. Um, so binding energy by itself isn't like super useful to understand why fission and fusion happen, but if we think about binding energy per nucleon, it does help us better understand it. And that's what this plot is. This is a plot of the, oops, of the average binding energy per nucleon as a function of the mass number A of the particular nuclei that we're talking about. So if we think about it low mass numbers like 0 to 10, you get some of these kind of crazy wiggles and spikes. That has to do with some magic number nuclei in the low A range. Um, in the Google Drive in the resources section, I posted chapter 1 of the LaMarche book. He does a discussion about the magic numbers of nuclei, and I think it's kind of interesting. Like, this curve doesn't really follow a smooth curve because of these outliers. Like, helium-4 is what's responsible for this first spike. Carbon-12 is what's responsible for this next spike. Um, just like in chemistry, you know that the electrons around a nucleus, the electrons of an atom, kind of influence what kind of chemical reactions that element can have. The so and we know that there's a structure to the electron cloud, right? Like there's different energy levels that that electron cloud has, and certain elements are more likely to have reactions based on how that electron shell is filled. Like you've got the noble gases where their electron shell is fully filled, and that means that they don't really want to participate in any kind of interactions. It's very hard to move their electrons because they've got fully bound electron shells. The nucleus also has a shell-like structure, and the nucleus also fills itself in a similar kind of way. So you can have nuclei that have a fully filled nuclear shell, and that means that they are much less likely to participate in nuclear interactions. And so that's what happens with helium-4 and with carbon-12. They have full nuclear shells, which spikes their binding energy per nucleon. Their nuclear shell being full means that they don't really want to participate in nuclear interactions. It takes a lot more energy to pull and bind to pull a nucleon out of those guys because they have a very tight nuclear shell. Um, so that's what happens at the low numbers. If you get to around A equals 60, like around iron, that's where this curve peaks. So iron 56 has like a very high binding energy per nucleon, as we can see on this chart. And then as you go past 60, it kind of slowly and smoothly decreases. And so What the binding energy per nucleon kind of tells you about is effectively how tightly bound those nucleons are to the nucleus and to the nuclear structure. And it means that it requires more energy to separate them if you want it to. This is how this chart is always shown, but I kind of think that it's more helpful to almost invert it. So like this is just an inversion of that chart, but it's the same axis. So this right here would correspond to like H2, and then like over here we would have like U235. And so if you think about fusion, like you can take two atoms of hydrogen and fuse them together to make helium. And so if I took H2 and H2 and I fused them together, I would get helium-4, which is going to bring me down this way that I'm writing the chart. And so it's almost like thinking about you put a ball on a ramp and then you let it go. If it can roll down the hill, then that's kind of telling you like where those nuclei are going to get to a more energetically stable position. So the fact that you can take hydrogen and fuse them together to make helium means you're going down this curve, which makes those fusion reactions energetically favorable because you're doing a reaction that's going to result in going down the curve or result in things that have more binding energy than what you started with. So that's like what happens with fusion. With fusion. And with fission, it's a similar thing. I've got a heavy nucleus like uranium-235, and I want to split it into pieces. So when I split it into pieces, I get two quantities, like somewhere around here, two different fission fragments that come out of that fission reaction. And to do this, I'm also going down the binding energy curve, which means that when I have fission reactions, I'm going down that binding energy curve. I'm getting to a more energetically stable state because I'm producing quantities that have a higher binding energy than what I started with. So generally, what we can say is that if a process results in the formation of a more stable nucleus, if a reaction produces nuclei that have higher binding energy, then that process is going to release energy. And that's why fusion releases energy, and that's why fission releases energy too. So if what I just said is true, you might be wondering, like we just said, fission is an energetically favored process. Why don't atoms just spontaneously fission if that's gonna what make if that's gonna get them to a more stable state? The ball rolls down the hill to get to a more stable state. Why doesn't the nucleus just spontaneously fission to get to a more stable state? And actually it does. There spontaneous fission does happen, but there's the strong nuclear force, which is acting to keep that nucleus together. And to overcome that strong nuclear force, there's a very high potential barrier that you have to overcome for that nucleus to spontaneously fission. So that barrier is very high, but the nuclei can actually it's possible for these to overcome that potential barrier just through quantum tunneling. And so as a result, different nuclei do have a possibility of doing spontaneous fission. Some of them are just more likely than others. So for uranium-235, the half-life for spontaneous fission is about 6.5 times 10 to the 15 years. So uranium-235 basically doesn't spontaneously fission, but californium-252 is a very special nuclei, and its half-life for spontaneous fission is about 66 years, which might not sound, it sounds like a large half-life, but yeah, that is small enough that you can actually take californium-252, put it in like a reactor, and it's just spontaneously decaying and emitting neutrons. They use californium-252 as a neutron source for that reason. Um, and so, yeah, if we want to make a reactor, we need a way to reliably get our uranium-235 to undergo fission reactions to overcome that potential energy barrier. And if you want to overcome that potential energy barrier, you kind of just have two options. The first one is to just brute force slam it with as much energy as possible. So you can make fission happen by just bombarding the nucleus with very high energy neutrons, bombard the nucleus with high energy neutrons. And when I say high energy, it's like many, many MeV. Um, the other way to do it is to let that nucleus absorb a neutron. If that nucleus would absorb a neutron, it gains some excitation energy from that event. So this will excite the nucleus, exciting the nucleus. And that excitation energy can then release the binding energy. So releasing binding energy. And that is the way that we make our reactors fission in commercial reactors. We don't really use high fast energy neutrons. We just let that neutron get that neutron to an energy where it's very likely that it gets absorbed in the nucleus. That increases the nucleus's it excites the nucleus and gets it over that potential barrier to allow it to fission and release its binding energy. And there's a couple different kinds of like characterizations of nuclei in terms of are they going to fission? Are they going to do something else? And so nuclei that can surpass that fission barrier just using binding energy are like the nuclei that we normally think of as fissile. So this is what it means for a nucleus to be fissile. It's material that can surpass and that binding energy barrier that can make fission happen just with like a low energy neutron. Um, and there's other nuclei that need that basically need some extra push to get there. They can fission, but they need neutrons of relatively high energies to make them fission. And so these are called fissionable. So like uranium-238, when we talk about like enriched uranium, it's just based on uranium-235. Uranium-238 actually can fission. You just have to hit it with a really high energy neutron. So these kinds of nuclei are called fissionable. And then there's some nuclei where they can absorb a neutron, go through a decay chain, and then become, through that decay process, something that is fissile. And those nuclei are called fertile. Fertile nuclei are the ones that can become fissile after they absorb a neutron. So that is some of these overlap each other, right? Like thorium-232 is technically fissionable. If you hit nuclei with a high enough energy neutron, you can make them split. But also that thorium-232, same thing with uranium-238, they can also just absorb a neutron, do some transmutations, and then become something that can fission. So in the case of like thorium, it absorbs a neutron and it goes through the decays and it eventually becomes uranium-233, which is fissile. And uranium-238 can absorb a neutron, go through some decays, and eventually become plutonium-239, which is also fissile. So I wanted to talk a little bit more about just the fission process, kind of like this cartoon is showing like a frame by frame um, images of the fission process. So the first thing that happens is that neutron gets absorbed and that neutron goes into the nucleus, excites that nucleus, and you get an excited nucleus. So that's what's happening in this first part. That's right here. Scission is the process by which that nucleus begins to split into two pieces. And this process is very, very quick. So this scission process happens in about 0.01 picoseconds. And that's what this is showing. That nucleus splits into two. Once that nucleus has fully split, these fission products that come out are very, very unstable. They're so unstable that they're immediately trying to get to a more stable place by just kicking neutrons out of their nucleus. And the neutrons that come immediately out of the fission process are called prompt neutrons. These get emitted in about, from there, they get emitted in about 0.0121 picoseconds. And the prompt neutrons that come out of fission they contain about 5 MeV of the total energy associated with this process. So the little green guys are neutrons coming out. Um, pretty much almost immediately after the fission process, you get prompt neutrons, but you also get prompt gammas that come out. Those happen about on the same time scale as the prompt neutrons, so like 0.01 to 1 picoseconds, and they contain about 7 MeV of energy, which is kind of interesting that the gammas actually run away with more energy than the neutrons do. Um, and once these fission products once these fission products have split and they've emitted their neutrons and they've emitted their gammas, the kind of thing that we also want to just kind of conceptualize is that like if you have a solid like piece of uranium fuel like those UO2 pellets, um, the fissions that are happening are within that structural material. So it's like you've got a location in that lattice where you've got a uranium 235, and then that uranium 235 is fissioned. It's split in half, and what it used to be is now basically emitted. There's a lot of energy released, and that means that those fission fragments are flying away from each other with quite a bit of energy, but they're stuck in this material lattice, which means that they don't like leave the material, hopefully. They just end up quickly getting stopped. They're ions, so they have a lot of electric charge, and that means that they get quickly stopped by Coulombic interactions with the other nuclei, with the other stuff in that lattice. And so those fission fragments get stopped in about 10 picoseconds. And the fission fragments carry away the bulk of the energy. They carry away about 165 MeV of the total fission energy. So the vast majority of the energy from the fission process comes just from the fission fragments stopping. And like if you imagine this happening and all of that energy being deposited in a pretty small like amount of both amount of time, and they also it happens over a very short distance, that you can imagine is going to cause the material to heat up because that energy is basically just going to heating up all of the surrounding material. And then later on, once those fission fragments have stopped, they're usually still highly radioactive, and that means that they are going to continue to decay. And as those fission products and their daughters decay, this happens over a much longer time scale. It happens over like it depends on the nuclei, right? Like it can go from 1 second to many years, depending on which um, which which fission products we're talking about. And that's where like the radioactivity of our spent fuel comes from. Some of those nuclei decay relatively quickly. Other ones take a long time to decay. And so that's partly like that relates to our considerations about like how we store spent nuclear fuel and things like that. And these fission products and daughters decaying are contributing to about 25 to 30 MeV of the total fission energy. And I already said those fission fragments, they slow down due to the Coulombic interactions. You've got charged particles moving through a medium. They're interacting with all the electron clouds that causes them to be emitted, be splitting apart from each other, but then very quickly stop. All of that energy gets deposited into that fuel, which makes that fuel heat up. And so in this process, they convert their kinetic energy into thermal energy. In other words, heat. And the total amount of energy released in a fission event is about 200 MeV. At least for uranium 235, it's about 200 MeV. So that's the sequence of events that happens in a fission process. It's important to just kind of understand that this happens very quickly. All of that energy, more or less, goes into heating the material. It also produces neutrons, which can then be used to make our chain reaction happen, because these neutrons can then go and hit another atom of uranium and then make it fission, and then we can continue the process. So just some check your understanding questions about fission. Um, does all of the energy that is released by fission go into heating the reactor? In other words, is all of the energy coming out of fission recoverable? What do y'all think? It's not. And how come? Right, yeah, exactly. Some of them escape, right? Some particles leak. Some particles leak, and those carry away energy. Um, Neutrinos come out of fission. They are part of that that chemical or that nuclear reaction. So neutrinos basically don't interact with anything. They take their energy and they leave. Some gammas can escape, like some percentage, like a low percentage of gammas and neutrons can leak from a reactor. Those will also carry away some of their energy. Um, the next question, if we have a reactor that's been operating at full power for a long time, and then we scram the reactor and turn it off, that means that we're stopping the fission reactions from happening. Have we still stopped all of the heating of the nuclear fuel and the structural materials once we shut off the fission reaction? No. And how come where's the energy continuing to come from? Perfect. Exactly. Perfect. We have decaying fission products that we still have to account for. Decaying fission products continue to release energy. Um, if we think about what fraction of the power comes just from decay, we had said before that it's about 25 to 30 MeV is what's associated with the fission products and their daughters decaying. But like about half of this is all neutrinos, which just immediately escape. So if we take half of that and then divide by the total, that means that we've got about like 13 to 15 MeV over the total 200 MeV. And that comes out to like 5 to 6% of the total. So decay actually makes up like a pretty decent amount of the reactor power. For reactors operating at 1,000 megawatts, 5 to 6% of that is just from the decaying nuclear fuel. So, and I just kind of answered part four. That is partly that's the main reason why we still need to keep reactors cool even after we've shut them down. So yes, because if you think about 5 to 6% of 1,000 megawatts, the large power reactors that we have in the United States, like the AP 1000 reactor, its power rating is about about 1,000 megawatts. 5 to 6% of that is like 50 to 60 megawatts. And like right now, there's small modular reactors that are like talking about how they're going to make these little baby reactors that are going to be like the argument is that making them smaller is going to make them more economically viable or at least easier to construct them. But like that, a lot of these small modular reactors are producing an energy that's on the order of like just what a large reactor is producing from decay. So it kind of helps put into scale just how large these big power plants are. And yeah, I think that that's kind of interesting. Um, so yeah, that decay is a big part of why we have to make sure that we keep our systems cool. Even after we shut them down, we've got to keep them cool for a while. Otherwise, we run the risk of our materials melting. Um, when we think about fission reactions, the other thing that we can think about is what the fission products look like. This plot is the fission yield curve or the mass fragment distribution. And so on the vertical axis, it's a probability. And on the horizontal axis, it's basically saying what's the probability that I get a neutron a fission product out of fission that has a given mass number. So like this mass number right here is very energetically favored. This mass number right here is very energetically favored. You might think that when fission happens, that those fission products have like an equal 50-50 split, but it's actually more like a 1/3, 2/3 split, as what we can see here. That's what's most likely. And the red curve is the mass product distribution from thermal neutrons. If you increase the energy of the neutron that's causing the fission, it kind of reduces how much you peak down. So this curve right here is showing the fissions caused by 14 MeV neutrons, whereas the red one is fissions caused by thermal neutrons. And if you were to continue increasing the energy from there, eventually you would just get a single humped distribution where it would preferentially split things 50-50. Um, so it's important to recognize that this is a distribution. So even though these kind of mass numbers are more likely to come out of fission, that doesn't mean that other nuclei can't come out. You can still get nuclei over here. You can still get nuclei over here. They're just much more or less probabilistically to occur. And I think that's pretty cool because what it ends up meaning is that if you think about nuclear reactor fuel, as that reactor is operating and as those nuclei are splitting, you're producing like everything on the periodic table. Anything like under uranium 235 technically could come out of a fission reaction. So in your reactor fuel, you can have gold, you can have platinum, you can have nickel, you can have all kinds of stuff in there because that fission product distribution can basically produce anything in this mass number range. So now that we've talked about fission and we've talked about that fission process, we can think about the life history of a neutron coming out of a fission reaction, or just like tracking a neutron in our reactor. So if we have a neutron in our reactor, it has an ultimate fate. It basically can only do two things in its ultimate kind of history inside of our reactor. The first thing that it could do is just be absorbed into something. So absorption is one ultimate fate of a neutron in a reactor. Maybe it gets absorbed into uranium, maybe it gets absorbed into like the structural materials. But it could be absorbed or it could leak. And that means that it leaves the reactor. There's technically a third option, which is that neutrons, like a free neutron, actually has a half-life, and a neutron can has a half-life that will make it decay into a proton and an electron and an antineutrino. But we can actually ignore the decay of neutrons. So they decay, but yes, we can ignore it, and we can ignore it because the half-life of a neutron is on the order of like 10 minutes. So if we think about like that entire fission process happening on like the order of picoseconds versus those neutrons at some point later on decaying over like 10 minutes, that's a incredibly long time compared to the time scales of the fission process itself. So in nuclear engineering calculations, when we're doing balance equations, we pretty much always ignore the decay of those neutrons because it happens over such a long time frame compared to fission. At least the neutrons that come out of fission. And if a neutron leaks, then we can't do anything about it. It's gone forever. We don't care about it. But if it gets absorbed, there's kind of two main things that absorbed neutron can do. If it's absorbed, hopefully it will make something fission, so it can induce the target atom to fission. That's what some of those absorbed neutrons can do. The other thing that they could do is they could be absorbed by something but not cause a fission. They could absorb into something and just have like just be a radiative capture event. So it can absorb and not fission. But what that means is that it's going to be absorbed into that nucleus. So it's going to increase the atomic number of the nucleus. And then eventually that excited nucleus is going to emit something to get back to an energetically favored state. So they're going to end up emitting stuff like a gamma ray. Um, and so yeah, that's basically if the absorption happens, those are the two options. And on the way to that ultimate destination of either absorbed into something or leaking out of the reactor, it can go very far without having any interactions at all. So these neutrons can just move arbitrarily arbitrarily far without interaction. It's kind of like when we were talking about the incident intensity decreasing exponentially. That decreasing exponential can't ever really go exactly to zero. The limit as x goes to infinity would approach zero, but a neutron could theoretically go very, very far, like light years through a material without actually having an interaction. Um, and the other thing that they could do that wouldn't be a leakage or an absorption is they can scatter off of stuff. So they can also scatter. And when the neutron scatters, like a billiard, when you think of scattering, just think of a billiard ball collision. Um, and that scattered neutron is going to lose, or really, it will change its energy, changing its energy. And we had kind of talked about before with scattering that there's lots of different scattering reactions. We can mostly just think of it as either being elastic or inelastic scattering. And elastic is when the kinetic energy is conserved mostly. Inelastic means that the kinetic energy would not be conserved. And it's the kinematics of those reactions which influences what the scattering reaction looks like. Um, so that's what's going to dictate like how much energy gets lost and how much. So if we could remove all of the neutrons from a reactor and then make some nuclei fission so that we produced exactly n numbers of neutrons, we could talk about that first generation of neutrons coming out as a generation. And those neutrons that come out of that fission could then interact with things, make more fissions, and produce more neutrons. And so we call the next generation the child neutrons from the parent generation. And some of those child neutrons can get absorbed by things that might make them fission. They could get absorbed into things that might just increase the atomic number and make a radiative capture event. Some of those neutrons might leak. And so that kind of leads us to two definitions, like the most common definitions of the multiplication factor, which is the number of neutrons in a new generation divided by the number of neutrons in the previous generation. That's one way to think about it. In terms of mathematically, it's probably easier to think about it in terms of the production rate of neutrons divided by the loss rate of neutrons. And then mathematically, we can say in general, P of t is the notation we can use for that production rate. And then L of t is the notation that we can use for the loss rate. And we've probably already seen what it means if k is greater than 1, equal to 1, or less than 1. And I'm just going to talk about in terms of the production rate. If k is greater than 1, it means the production rate is greater than the loss rate. Oh, guess we're out of time. But I guess we could just fill these in real quick, right? K greater than 1 means that we would call that configuration supercritical. If our production and our loss are perfectly balanced, we call that critical. And if our losses are greater than the production, then we call that subcritical. That is time. Thank y'all for your time. I hope you guys have a good rest of your day. If y'all have any questions about anything, please let me know. If you have questions about the problem sets, questions about the lecture, questions about anything else, feel free to let me know. I didn't get through all the slides that I had for lecture 2, so hopefully when we come to lecture 3, I'll be able to get us back on track in terms of finishing things up. At least finishing up the slides that I give you. So yeah, y'all take care. If you have any questions, please let me know. And if not, I'll see you guys on Wednesday.